Good morning students. In the last lecture we learned about the self-induction. Today we are going to discuss very important property. It is called as the mutual induction. We see that in the case of self-induction, whenever there is a change in the current in the coil, the magnetic flux associated with the same coil also get changes. So the change in current and the change in magnetic flux takes place in a single coil. But in the case of mutual induction, whenever there is a current passing through a coil, the effect will be obtained in the neighboring coil. Whenever there is a change in the current in the coil 1, the EMF induced in the coil 2. So we can say that the EMF induced in the coil 2 is totally depend upon the current passing through the first coil. Okay, so how we can define this mutual induction? Mutual induction can be defined as the production of induced EMF in a coil 2 due to the change in the current in a coil first, or whenever there is a change in the current in a coil first, there must be an EMF induced in the second coil. So such type of phenomena in which the effect is shown on another coil due to a current in a first coil, it is called as a mutual induction. Now, as we derive a very simple relation for the self-induction, coefficient of self-induction, in the same way we are derived here a equation for the coefficient of mutual induction. So how we can define or how we can derive the relation between the EMF, the flux, the current and the coefficient of mutual induction. So here consider that a current I1 is flowing through this coil first, and due to this current a neighboring coil in coil 2, a magnetic flux produced in it. Suppose that the current in the first coil is equal to I1 and the magnetic flux produced in the coil 2 is equal to phi 2. Here this 1 and 2 they denote the magnetic flux and the current produced in the first and second coil respectively. So as we stated earlier, the magnetic flux associated with the coil 2 with respect to 1, or we can say that due to the effect of coil 1, we can say that this phi 2 is directly proportional to the current in the first coil. So we can write here this phi 2 which is equal to, or we can say that is directly proportional to the current I1. So here we can write this phi 21 is equal to, it is M21 multiplied by I1. So what is this M21? This M21 is the mutual induction produced in the coil second due to coil first, or with respect to coil first. So this phi 21, what is phi 21? This is the magnetic flux passing through the second coil due to the current flowing in the first coil. So phi 21 is equal to M21 multiplied by I1, where this I1 is the current flowing through the first coil. Now, as we know, according to the Faraday's law, E is equal to minus d phi by dt. So how much EMF induced in the second coil? So we can write here this E21 is equal to minus d phi 12 divided by dt. So this E21 is equal to minus ddt of phi 12. So what is phi 21? It is equal to M21 into I1, which is equal to minus M21 into di1 by dt. So this much of EMF is induced in the secondary coil or second coil due to a current I1 is passing through the first coil. So this is E2 is equal to minus M21 into di1 upon dt, where this M21 it is the mutual induction. So how mutual induction can be write? This mutual induction 21 is equal to E21 divided by, it is di1 upon dt. So what is the mutual induction in the second coil? It is equal to, it is the ratio of the EMF induced in the second coil per unit change in the current in the first coil. Now if we keep this di1 upon dt is equal to 1 ampere per second, means the current is changing at the rate of 1 ampere per second, then this M21 is equal to E21, means the mutual induction is equal to the induced EMF is equal to the induced EMF where the rate of change of current in the first coil is equal to 1 ampere per second. Okay, so this is M21 is equal to E21 divided by di1 upon dt. Similarly, if the effect is reversed, for example, some current I2 is passing through this coil 2, due to that effect the magnetic flux developed in the first coil. The magnetic flux is developed in the first coil. So we can say that the mutual induction of the first coil due to the second coil can be written as this M12 is equal to E12 divided by di2 upon dt. So what is this M12? This M12 is nothing but the mutual induction produced in a first coil due to the current passing through the second coil. And what is this? This is equal to E12. What is E12? This is the induced EMF in the first coil due to the current I2 passing through the second coil. So this M12 is equal to this. By symmetry, we can say that the value of M21 and M12, they both are same. So we can write here this M12 is equal to M21, which can be denoted by a letter M. So the mutual induction of both coils with respect to each other will be same. Okay, now we write M12 is equal to M21 is equal to M. Now we know that what is M21 is equal to, what is M21 is equal to, it is equal to phi 21 divided by I1. And similarly we can write this M12 is equal to phi 12 divided by I2. So, but we know that this M12 is equal to M21, so we can write here this phi 21 upon I1 is equal to phi 12 divided by I2, which is nothing but a constant which is equal to the mutual induction M. Okay, so this is M is equal to this. So what is M and how we can define this mutual induction? The coefficient of mutual induction can be defined as it is the ratio of the magnetic flux associated with the coil per unit current passing through another coil. For example, this is phi 21. So this magnetic flux is related with the second coil and the per unit current passing through the first coil. In the same way, this is the magnetic flux produced in the first coil per unit current passing through the second coil. The ratio of both these magnetic flux per unit current is remains constant, which is equal to the magnetic or the coefficient of mutual induction in this case. Okay, now what is the unit of this mutual induction? The unit of mutual induction can be found out by using this equation, simple equation. This is the EMF, and we know that the SI unit of EMF is equal to volt. This is current, that is ampere per second. So we can write here, this is ampere volt ampere per second, which is also equal to, it is also equal to Henry. So we can write it is Henry. Okay, and it is denoted by a letter capital H. So the SI unit of the coefficient of mutual induction is equal to Henry. Also we see that in the case of self induction, coefficient of self induction, the unit is also Henry. So mutual induction as well as the self induction, they both have same unit, that is equal to Henry. Now we are moving towards the application or the coupling constant or coupling coefficient between the two coils. So what is coupling coefficient? Coupling coefficient is the measure of the flux which can pass through the second coil which is in vicinity of the first coil. Okay, so how much magnetic flux reach the second coil which is in vicinity of the first coil? This measurement is done in the terms of coefficient of coupling constant. Okay, so we can say that this coupling constant, we can find out a simple equation for that, and for that we know that for finding out the coupling constant, we know that this mutual induction is proportional to, this mutual induction or the coefficient of mutual induction is proportional to the EMF in the second, or the EMF induced in the second coil. Okay, how? This M21 is proportional to E21 and M12 is proportional to E12. So we can write this M is proportional to E2, that is the EMF produced in the second coil. Now we know that this E2, that is the EMF produced in the second coil, is proportional. It is proportional to the induced EMF is proportional to the magnetic flux associated with the first coil, as well as it is also proportional to the number of turns in the second coil. So we can say that this E2 is proportional to phi 1 into N2. So if this E2 is proportional to the magnetic flux in the first coil, as well as this E2 is proportional to the N2, that is the number of turns in the second coil, then this E2 is proportional to phi 1 multiplied by N2. But what is phi 1? This phi 1 is the magnetic flux associated with the first coil, which is also equal or which is proportional to. So we can write this phi 1 is proportional to, it is proportional to the number of turns in the first coil. So we can write this E2 is proportional to N1 multiplied by N2. Okay, E2 is proportional to N1 multiplied by N2. But what is N1 and N2? N1 and N2, they are the number of turns in the primary coil and number of turns in the secondary coil. So how we can calculate? We know that in the self induction we find out that this L is proportional to the square of the number of turns. That is, L is proportional to N square. Therefore we can write this L or this N is proportional to under root of N. So this N1 is proportional to under root L1. Similarly, N2 is proportional to under root of L2. So we can write here, therefore this N1 into N2 is proportional to, it is under root L1 multiplied by L2. So therefore this EMF E2 is proportional to it is proportional to under root L1 multiplied by L2. Or if we drop this proportionary sign, then we write here a constant k. This k is equal to, or this k into under root L1 multiplied by L2. Now this EMF E2 can be replaced with this magnetic induction, mutual induction. So we can write here this M is equal to, it is k into under root L1 multiplied by L2. So here this k is called as a coefficient of coupling between the two coils. It is the coefficient of coupling between the two coils, coil first and coil second. The values of k, if the values of k are changed, then the binding between the two coils can also be determined. If the value of k is greater than 0.5, if the value of k, coupling coefficient k, is greater than 0.5, then we can say that the two coils are tightly bounded. They are tightly bounded. Then if the value of k is less than 0.5, then you can say that they are loosely bounded. And if this L1 is equal to L2, then we can say that this k is equal to, or this L is equal to M. So by knowing the value of coupling coefficient, we can say that how these two coils are bounded with each other. Either they loosely bound or either they tightly bound. But this coupling coefficient is also depend upon, how these two coils are inclined to each other and how far they are from each other. Okay, if the value of k must be in a desirable value, then two coils must be in line and they are far apart from each other, so that there must be no interaction between the two coils. So in this way, today we discuss all about the mutual induction and the properties of the mutual induction. Also we see the coupling coefficient between the two coils. In the next lecture, we are going to find out, or we are going to discuss a very important application of the mutual induction, that is nothing but the transformer. Okay, so this is enough for today. Have a good day. Bye.